Morning. Welcome to Krishna's classroom. The topic we plan to discuss today is the step function approximations or simple function approximations of measurable functions. So this is the topic that we get working on. Now, before I actually enter this topic, we should spend some more time on the theorem or the proof of the theorem that we proved last time. So recall that we proved the following theorem. So this was the theorem 9 we have proved. Let Fn be a sequence of measurable functions on some measurable set E, which converges pointwise to, and what you say is that F is. So I think we have talked about this proof. We have even given the proof, and the crucial step is to prove that F is measurable. So what you have is that Fn converges to F infinity pointwise. That means Fnx. That means Fnx converges to Fx for every x. As n tends to. The consequence is that we are not assuming very strong convergence like uniform convergence or anything, but what we are proving is that, see, Fnx, the sequence Fnx is a sequence of numbers which converge to a number, and that number is what you call, so F is it's a convergence sequence. Now this in turn means that given epsilon positive, there exists n such that now this n generally depends on x, because we are assuming only pointwise convergence. So n depends on two things, namely n is a function of epsilon and x. That is what. Now, what we wanted to prove was that such a function is measurable. Therefore, we have to say, so the question is, can be translated into what is the status of this? What is the status of all x belonging to E such that fx is less than c? Or this is the question. Okay, status of this. This is the question that we want to solve. Therefore, we have to see what we have is this f comes as the limit of fx. Okay, so we have to work with the following, and I have said a lot of things about it, but eventually this is what happens. So we have to, I said that see, it's almost everywhere in the statement of the theorem. Therefore, on a set of E naught, that this may not converge. But so you take E slash E naught. Now take the restriction of f to the E minus naught, etc., etc., and then use the theorem. So if you can prove the convergence there, that this is measurable, then you are done. But for that, without loss of generality, we assume that we are everywhere on E works. So everywhere on E minus E naught, if you can prove, then in the restrictions you see that you can get the same result almost everywhere on the interval, on the set E. So this is what we want to examine. This particular set for an arbitrarily chosen C. Okay. So this we have to first write it, because the information that we have is that we don't know anything about f. F is the limit, pointwise limit of the sequence fn. Okay. So we will get the following results. Okay, so we can write this as you know that there is an n such that this is true. So let us change the notation. So we have fjx one by n. We take epsilon to be this, or j greater than or equal to some k. This is what you have. Okay, so we make use of this, right? Therefore, what we have is this, that on this side, this is the question that you are asking, is this equal to this? Now you see, to take the set k, say j equal to a to e, set of all x belonging to E, for which fx, fjx is less than c minus 1. I will explain the logic for this. Now you take this and then take the union of all this for over k n 1. Write this. If you are successful in identifying these two sets, then you are done, because you see that this one is a measurable set. This is a measurable set. Therefore, this is a countable intersection of measurable sets. Therefore, it is measurable. And then you are taking the countable union of measurable sets. Therefore, it is measurable. Therefore, this is measurable. So that's the question. That's how we solve it. Okay, but how do we come across this kind of arguments? Now, this is what we have to identify these two sets. So I put a question mark. I am not identifying them, but this is what I am trying to do. Okay, so essentially the problem is you have two sets. A defined as and B identified as union intersection So what we are going to claim is that A equal to. So we have to prove essentially. This is for the sake of students. Okay, how to prove this kind of things, and then we have to prove B is contained in. You can prove both. Then that implies A equal. So we have to prove either of them. So how do we prove this? This is the strategy. Now you see, let us explore this a bit. I just some function. This. Now you see that this is now let me draw a line, something. This is the particular C that we are in, and then this is C minus 1 by 12. Okay, and now when you let n tend to infinity, that C minus 1 by n goes to C. So when you do this for all n, you see that you get all the situation, you get a sequence through which you reach here. Okay. So what happens? You see that suppose x naught is this point, then you see that this is your and what about fj? So you have fj x naught converging to fx naught. So what happens in this case? In this case, you see that this is your fx. In this case, what happens is, see, the fx less than c happens here only, on this set and on this set. So this is the. So it happens here as well as here. Okay, and fx. Okay, what happens to fjx? So you see that if you take fx less than c minus 1 by n, take the union of all that, you will reach it. You get this set. Okay. So we will work out this. What happens here? Suppose x naught is here. This point is not in the collection of points at which fx is less than c. It's actually fx naught is greater than c. So here fx naught is greater than c. Then what happens? What about the fj's? Fj's converge here. So what happens is that look at the collection fjx naught. Now you see that there is some neighborhood where all these fjx naught crowd around. Okay, that is what you call some k. So what happens is that you can find a k such that for all k, for all j greater than k, that fjx naught minus fjx naught minus fx naught is, or fjx naught is greater than c. That's the condition. So if the point x naught is such that fx naught is greater than c, then you see that fjx naught is also greater than c from some j onwards. Okay, as it is clear, because fjx naught converges to this. So these points have to be avoided. Now what is to be brought in? The other point that is to be brought in is this. Now what happens? What are the points that are likely to come? All the points. Now you see, you take one particular n. So c minus 1 by n. See, these points are inside this. So you see this. These points are inside this. This set is inside this. This set is where you see that fx is less than c minus 1, right? This has to be there. Okay. Now in this case, what happens is that if you take an x naught here, suppose you choose the point x naught here, what happens here? Here you see that there is a gap between fx naught and c minus 1. Therefore, see, you can find some neighborhood here into which all these fjx's get closer to fx naught. Or what happens is this fjx naught is less than c minus 1 by n, and that's how this comes. Okay, so such x's you choose. Okay, right? And then you take the union for all possible k and for all possible. This is what happens. So let us analyze this. Right. So what we want to prove is identify if an x belongs to. So let us start with an x belonging. If x belongs to A, then f of x is less than c. Okay. Now we fix the point. Let Let us focus on the point. So that you have fx naught strictly in a sense. Then there exists an n such that c minus 1 by n is greater than okay. Right? There is some gap between these two. So you take c minus 1 by n and since fjx converges, so we are going to bring those fjx x naught over there. So what you have is, see, this is a very simple fact. Okay. See that we'll have to choose n sufficiently large such that c minus 1 by n is greater than 1. So this is this. Okay. You take c minus 1 by n, it is some point here. Okay, so there exists a point c minus 1 by n such that c minus 1 by n is greater than fx naught. That is, in between there are infinitely many points between fx naught and c. Therefore, this is okay. Now, what one does is this. Okay. So choose epsilon to be equal to c minus 1 by n minus fx naught. Then this is possible. That is possible. That means you choose an epsilon equal to this one. This is the epsilon neighborhood of fx naught. Okay. Now what happens? Fjx converges to fjx naught converges to fx. So fjx naught infinity. This implies given epsilon positive, that means you choose this epsilon, there exists k positive, a natural number such that equal to. Now this is purely the definition of convergence at the point x naught. Now you see, let us take one part of it, that is fjx naught minus fx naught is less than epsilon implies and this is equal to, what is it? C minus 1 by n minus fx naught implies fjx naught is less than C minus for every j greater than. So if fjx naught is less than fx naught, then this implies certainly less than C minus. Okay. This is the situation where fjx naught is greater than fx naught. So this is where we are assuming fjx naught then you need a k, otherwise for all j this is true. Therefore what you have, therefore which implies x naught is an element of B. That means for it is in one of these collections, k to infinity is 1, therefore it is in, okay, because this is in the intersection j equal to k to infinity x belonging to E, fjx less than C minus 1. So that is there. So x naught belongs. Okay. What does this mean? This implies A is continuous. So what we have done is, we have taken a C. Now there is a C minus 1 by n which is less than this, okay, which lies between fx naught and C, okay, and then you see you can find an epsilon we have constructed here, for which there is a k, etc., etc. So all these things are true. Now what we want to prove is, so that proves one part. The other part is that we want to prove D is contained. So enough to prove that x naught not in A x naught not in A implies not in. So that whenever x naught is in B, it is there. Okay. So this is the strategy. Okay. What do you mean by x naught does not belong to A? X naught does not belong to A if f of x naught is greater than or equal. So there are two situations now. One, fx naught is greater than C. The other one is fx naught is equal to C. Both the cases are. We will analyze them. That is, first case, fx greater than C. Second case, or equal to, we will analyze both these situations. Okay. Now let us go to the picture what we have. Suppose x naught is such that fx naught is greater than c. This is a point where x naught for which fx naught is greater than c. This is fx. Now what happens is that, you see, then fj x naught converges to fx naught means that after some stage of j, you see that fj x naught is greater than c because it falls on this path. See, fj x naught will be either here or here, fj. So from some k onwards it is going to be, greater than c. So that's the argument that you make. This implies there does not exist k such that c, okay, therefore you see that is fj x naught is greater than c for every j greater than k. That's always there. There is such k. So that does not exist such that exists. Or in general, c minus 1. Okay. Therefore, what happens? Which implies x naught does not belong to, that is, x naught belongs to the complete. That is the complement. Okay. Now what we analyze is the case 2 where fx naught equal to c. This is the see, this is a point C. So this is fx naught. Suppose x naught is this. So this is going to be fx naught equal to C. Now what happens? Choose n positive for c minus 1 by n. See, this is c minus 1. C minus 1 by n. What happens? Fjx is that means we are taking a neighborhood of, okay, this is your epsilon is 1 by. Implies such that for every j greater than k, fjx is fjx naught is greater than c minus. Once again, this implies x does not belong to, x naught does not belong to, that is x naught belongs to, okay, right? So what have we proved? We have proved two things. One, A is contained in B. Then we proved that A complement is contained in B complement. So we have proved that A is contained in B and A complement. Therefore, so together now you see that now implies B is measurable. Why it is measurable? Because it is first of all the intersection of measurable sets and then the countable union of that, therefore it is measurable. B is measurable. Okay? Which implies A is measurable. So that completes the proof of the theorem. But you see, this kind of analysis is something that one should go through, and at least the students should learn how to make this analysis. Okay, so I have done just this. I can just hand wave like I did last time. Just write one line and go to the next step. But I thought, maybe on a second thought, I had a feeling that I should probably spend some time on it. I hope it is worthwhile, that you have understood how to discuss us. But one should sit down and analyze it. Okay. Now we recall that we have defined what is called a simple function. And this is actually what you have is this, that it's a phi which is equal to sigma the characteristic function of k this is the indicator function of the set E, where Ek is measurable and on Ek phi is equal to C. This is what you call a simple function. Now what we plan to prove, or what we are going to do, is to approximate measurable functions through simple functions. It's all the step towards proving or defining the integral, because for simple functions it is very easy to define the integral. Okay. So we are going to do that. We are on the right track. Okay. So this is the approximation of measurable functions using simple functions. Okay. So let us just recall the definition of simple function, or what we have written already. Now what we want to do is, we want to do a lemma. Or if you want, you can call it theorem. We call this theorem. So a limited use theorem, which is going to be used in the proof of the next main theorem. So let f be a measurable real valued function on C is a measurable set. Now we make the following assumptions. Assume f is bounded. on E with a bound M positive. Such that mod F for every x belonging to so it's a bounded function. Then for each epsilon positive there exist simple functions phi epsilon and psi epsilon defined on E such that F is squeezed between phi epsilon and psi epsilon, and that is on E, the difference between phi epsilon and psi epsilon is less than epsilon. So for arbitrary epsilon you can do this. So for each epsilon you get such simple functions, and then as epsilon goes to 0, you see that these simple functions get closer and closer to the function as indicated by these two results. Okay, so let us see the scheme. It's quite easy to do it. What we are going to do is this. Suppose you have a function whose graph is something like this. Okay. Now what we do is take some interval, say yk and yk plus 1. 2 points in the range. Okay. Now what happens? What about this function? This function has the property that it lies between yk and yk plus 1 here. It lies between yk and yk plus 1 here. Elsewhere it is not. So what we are planning to do is to make a lower approximation of this function over this portion by this line and over this portion this by this line. Okay, and an upper approximation on these lines, on these sets by these lines. So this is the part of phi k, psi k, and this is the part of phi. So on the inverse image of the interval yk to yk plus 1, you are defining the function to be defining a step function phi k on that set is going to be equal to yk, on the other set it is going to be, on the same set it is going to, psi k is going to be equal to yk plus 1. So let us, this is our scheme. Okay. So if you do it for every partitions, then you see that we are going to have step function coming up like this, and this over here. And then if you work on the next portion, it is going to be, this one will be the lower approximation that you have. And the upper approximations are going to be the following. On this set, it is going to be this over here, and over here it is going to be this. So you can see this part is the next approximation. Take on this portion the upper approximation, something. Take the function on this. So you see that this yellow step function is the corresponds to the psi k, and the what you call the reddish lines step function correspond to the function phi k. That's how you construct it. So let us now formally do this. Going to exploit let CD be an open in the range space such that the image of CD such C and D exists because you see that Fx is bounded. So such as because so actually Fx lies between minus m therefore you can easily find such a CD. Okay. right? That is E is CD. So let be a partition of the closed interval CD. Such that less than epsilon. Now let EK define F inverse of IK, where IK is the closed open interval yk minus 1 to yk. Now this for all less than or equal to n. Now define phi epsilon, it's all self-explanatory, minus 1 times chi k and psi k, psi epsilon to be equal to as I have described earlier, you see in that figure. Then for x belonging to CD, Fx belongs to is contained in now there exists a unique k one less than or equal to k less than or equal to n. These are all obvious, for which yk minus 1 is less than or equal to fx less than y, and which implies phi epsilon x equal to yk, which is less than or equal to fx less than or equal to less than yk, which is equal to psi epsilon x for x belonging to E. Now it is clear that we have yk minus 1 is less than epsilon, so rather equal to epsilon, and which implies less than epsilon. For x belonging to and likewise for every such thing less than epsilon. Therefore, now this is exactly what you. Therefore, you see that for every x belonging to psi epsilon this is exactly what we wanted, and this is a simple function. This is also a simple function. So these are the approximations that you can make for this. Okay, I stop here. Thank you very much.